All right, today is the 13th, 3/13/17, the eve of the blizzard, we hope. So potential energy is just energy that's been stored in some form. And outside of physics, we can talk about chemical potential energy, we can talk about all that, but here we're only going to talk about the forms that are what are called mechanical. So they are basically they are a result of either the position of an object or properties of the material. And, oh, hey, potential energy depends on the relative position of the object as well as the characteristics of the object itself, or characteristics of the material. So we have two basic forms of potential energy that we're going to talk about. The first is gravitational potential energy, or our old friend PEG, potential energy due to gravity. So this comes directly from how far away from a gravitational attractant force something is. So basically how far from the center of the Earth you are. But we generally just measure to the thing that you're going to hit, which is usually not the center of the Earth, unless we, do the video that David had about falling through the center of the Earth. In general, you're going to hit the ground. So we talk about height above the ground or height above a surface. And so the formula for potential gravitational energy is really easy. It's mass times gravity times height. Mass in kilograms, gravity, of course, in meters per second squared, and height in meters. And it is given in joules. And you can do the dimensional analysis on that. It works out. So here's the thing. I love arbitrary stuff. 0 is arbitrary. 0 is where you're going to hit. So if you are 20 meters above the surface of the Earth, but you're only 5 meters above a roof that's going to catch you when you fall, then your height is going to be given as that 5 meters. And you can think about something on your desk. Is the amount of potential energy that it's got different if we consider the desk as your 0 point? Yeah, what's the gravitational potential energy of that book if we consider the desk as a 0 point? 0, because the height is 0. Those desks are, about 0.6 meters high? So whatever the mass of your book is, times 0.6 meters times 9.81 meters per second squared. Is it different if we have a hole in this floor going down to Mrs. Halett's room? Wouldn't she be surprised if books suddenly fell out of the ceiling? Yes, she would. Perhaps we should work out a chute in the science rooms. That would be cool. That'd be great. Yeah, but the drain, that's a different matter. So anyway, no matter, if we're looking at something with the potential to fall different heights, it's got different amounts of potential energy because it's really about how far it can or will fall. Now we talk about P, potential energy elastic. We have PEG and P here. Elastic potential energy is all about deformation. So how far you can deform a material, and that material will then revert to its original condition. And I have one small sample piece here of our bungee stuff. I should tie a knot in this. No, I shouldn't. Okay, because I really can't. So I can deform this. It returns to its original length. Deform it, returns to length. Ooh, deform it, it returns to length. I can also snap myself with it. And this is where we're going to get into the K values. So the formula for potential energy elastic is 1/2 kx squared. Does that look visually like anything else you've seen recently? 1/2 mv squared, yeah. Oddly reminiscent. So potential energy, it makes it kind of easy to remember. X is the amount of deformation. It's the difference between this length and this length. It's how far you can deform the material. Now this is a material, this happens to be a material that's being deformed by stretching. There are also compression deforming elastic materials. Can you think of one?
Spring.
Well, you can have an extension spring, you can also have a compression spring. Yeah. So vehicle springs, truck springs are compression springs. Anybody do gymnastics? Yeah. The springboard in front of the vault is compression springs. There are other examples of compression springs, but those are some good ones. But we actually do deal more every day with extension springs. Oh, I guess a ballpoint pen has a compression spring in it. So that'd be another one. And then there's this K, this mystical K. K, interestingly enough, no. Stands for Katie. Yes, it's the Katie constant. No, it's not. I'm sorry. K is what's called the spring constant. And so the spring constant is a force constant. And the bigger the spring constant, the harder it is to depress or expand that spring, and the more energy you get out of it when it reverts to its original shape. So the stiffer a spring, the higher the spring constant. The looser a spring, the lower the spring constant. It is newtons per meter. And what that means is two things. How many newtons of force does it take to deform it 1 meter? And how many newtons of force, oh, this is going to hurt. Ow. Not that bad. Do you get back out of it when it is reverting? See, and I'm being really good because I haven't threatened the whole class with the giant rubber band yet. Aren't you proud of me? So, how many newtons of force do you get back out when it reverts to its original shape? And K is different for every spring. We can measure K. You might think that that might come in handy when you're designing bungee systems. Guess how we measure K? Meter stick on a spring scale. Pretty simple. So we'll go out and do a little bit of playing with springs in a little bit, but first let's look at one example. The original length was 42, and we extended it to 50 using 10 newtons of force. So if K, the spring constant, is newtons per meter, we have 0.08 meters divided by 10 newtons. What's the spring constant for that chunk of material? Lord, I can't do anything right. Not today. 10 newtons. Okay, there we go. So 10 divided by 0.08. 125? Yep. So that has a spring constant of 125 newtons per meter. And it's not a perfect way to measure, but it's not terrible. This would hurt if you got snapped with it. Something with a spring constant double that would hurt twice as much. Okay, we're going to practice sample problem 5D 179, then you're going to work on the 5D problems, and that's all we got.
That's it for chapter 5.
No. So, here's a place where I'm going to point something out. The book asks for total potential energy, and they then proceed to sum those two potential energies, regardless of the fact that the potential energy is in different directions. So we'll go through this, and I think there's a difference between net and total that they don't examine, so we'll kind of look at that. So to start off, we have the mass of the person, the K value of the bungee cord. Here's what we know. The PE total is equal to the potential energy due to gravity plus the potential energy elastic. So the peg and the P. And we can start off, the peg is really easy because peg is mass, gravity, height. We have mass, 70 kilograms, I believe. Gravity is 9.81 meters per second squared. And the height above the water when this person comes to a stop is... Oh, okay. So we have to do a little bit of figuring for this. When this person comes to a stop, they have a 44 meter length on this. So they are 44 meters down, and this total distance is 50. So they're 6 meters above the water. So potential energy due to gravity. Okay, so we have our potential energy due to gravity. Now, here's a question for you. Is that potential energy down or up?
Down.
Down, right. Because if we were to sort of cash in that potential energy, that person, that object, would be falling downward. Okay, just so we're all clear on that. Now, the potential energy elastic, I'm going to set this aside. Potential energy elastic is equal to 1/2 kx squared. So we're given k, we have to figure out what x is. X is the difference between stretched and unstretched length. So potential energy elastic equals 1/2 k, and whoops. This goes from 15 meters to 44 meters. So 44 meters minus 15 meters. And K, we're told, is 71.8 newtons per meter. Now here's my question for you. So we have the potential energy due to gravity. Is this up or down? Up. 29 squared times 78 point, because I put in 78.1, not 71.8. Duh. Okay, so we've got a raw answer that's correct now that I fixed my number reversal. Is this potential energy going to, if we cash this in, does this person, this object, move up or down? Up. So here's my question for you. Here's what your book says. Your book says, well, the magnitude of these two things, the PE total, is just the sum of these two. So that plus that, and we get 34312.1 joules. Anybody got a problem with that?
It's a big number.
Okay, aside from the fact that it's a big number. Yeah, I have an issue with that. Your book just does the total potential energy and it adds them together. I think that there's a place to talk about net potential energy in lieu of total. I don't think the total makes sense here because one would pull you down and one would move you up. You know, so at some point they, some part of them cancel. So for our purposes, I would say there's a net potential energy of 26,071.7 joules, and my sig figs are terrible here. What do I have, 3 to work with? How many? 2? 2 sig figs? 3 sig figs? 3, I think. So 26, geez Louise, I can't even write simple numbers. 26,1, there. 26,100 joules up. And your book doesn't treat it that way, and maybe I should post to the physics forum and put myself up for more critique.
Derision.
More derision. Well, obviously what you're missing. But, for my purposes, if I ask for total, add them. And if I ask for net, I think you subtract them. You find the net potential energy. I think that makes sense. Again, biologist. So that's it. All the problems in 5D are assigned. Question. Potential energy due to gravity was 4,120 joules.
Oh, okay.
And the elastic potential energy was like 30,000 some.
Oh, okay. I thought it was just...
So they're going to go flying upwards. And actually, this is probably, I'm going to guess that you really have to factor these calculations into bungee jumping. And on improving on the way we use the numbers in designing your harnesses to cruelly throw flour sacks off the balcony.
Does it depend on how much force we use to throw it off? Like,
oh no, you just push it off. You just drop. You don't want any. Yeah, you don't want to pitch it. Yeah, you just want to. Yeah, take that, Junior. Junior will die a gory, messy, flowery death. But yeah, I'm going to guess that the net potential energy on your jumper is a critical piece of your calculations in ensuring survival.
Is that a hint?
It's actually, no, it's speculation on my part because last year was the first year we did a real drop. It was only the second year for the project. And there were lots of things that I looked at and I thought, okay, I don't understand that well enough, so I'm learning with you. You know, but yeah, so it's speculation on my part, and thinking about the ratio between the potential energy due to gravity and the potential energy elastic upward, and how much you want to have at the point when you bottom out. So that's it. Work.